Welcome to this tutorial on recent developments in geometric machine learning foundations, models, and more. Throughout this series, we will explore how symmetry structure in data and tasks shapes the learning process in fundamental ways, leading to better data efficiency, stronger generalization, and more robust models. This tutorial was presented at NeurIPS 2025 by Stephanie Jagielka from TUM and MIT, and Biruz Tomasebi from Harvard. Welcome to this tutorial on recent development. Machine learning models encounter data that carries hidden structured data that remains essentially the same under certain transformations. Think of an image, shifted by a few pixels, and the content has not changed. Or a molecule, rotated in space, and its chemical properties remain identical. Or a set of points, list them in a different order, and the underlying object is the same. We call these transformations symmetries, and understanding them is a core challenge in modern machine learning. The first example is image classification. Shifting a picture by a few pixels does not change what it depicts, so the predicted label should remain the same. The second is molecular property prediction. Rotating a molecule in 3D preserves all of its physical and chemical properties. The third is set processing. A function on a collection of objects must not depend on the order they are listed. In each case, the transformation leaves the relevant information intact. These symmetries, when explicitly built into our models, have a profound impact. Models that respect symmetry require far less training data, because they generalize correctly across all transformed versions of an input. They generalize better to new examples, resist noisy perturbations more effectively, and are often easier to optimize and interpret. This motivates a systematic study of symmetry in machine learning. Welcome to this. Let us be precise. Given a function f, a transformation t is a symmetry of f if applying t to any input does not change the output. Mathematically, f of t of x equals f of x, for all valid inputs x. We call this property invariance. The output is invariant, it does not change no matter how we apply the transformation t to the input. This is the central definition we will build everything on. The simplest and most familiar example is image classification. If you shift a photograph of a cat a few pixels to the left, it is still a photograph of a cat. A good classifier must be shift invariant. Applying the shift transformation t cannot change the predicted label. This is why convolutional neural networks use weight sharing across spatial locations that encodes shift invariance directly into the architecture. The same filter detects a feature wherever it appears in the image. The second example comes from functions on sets or point clouds. A 3D point cloud representing an object is just a collection of points. There is no natural canonical ordering among them. Any function that correctly describes the shape must produce the same output regardless of how those points are ordered. This is permutation invariance, and it is the defining property of architectures like PointNet that process unordered 3D data. Welcome to this tutorial on invariance shows up across machine learning in surprising places. Let us look at two concrete examples, one from graph neural networks, and one from the internal structure of neural networks themselves. In graph learning, nodes have no canonical ordering. Permuting the rows and columns of the adjacency matrix A by a permutation matrix P simply relabels the nodes. The underlying graph structure is unchanged. Our model must therefore satisfy f of P transpose equals f of A for any permutation P. Two adjacency matrices related by such a permutation represent the same graph and must produce the same output. Even neural networks themselves have an intrinsic symmetry. In a two-layer network, permuting the neurons of the hidden layer, rearranging the rows of W1 and simultaneously rearranging the corresponding columns of W2 produces a network that computes exactly the same function. Here, each color represents one neuron. The same color in W1 and W2 belongs to the same neuron. This means neural networks do not have a unique weight representation. There are always infinitely many equivalent parameterizations. Both cases illustrate invariance. A permutation of the input leaves the function's output unchanged. These symmetries are hiding in plain sight throughout the models we use every day. In the next section, we will extend this idea to equivariance, where the output transforms together with the input. Welcome to this tutorial on With invariance fresh in mind, let's introduce a closely related and more general property, equivariance. Where invariance requires the output to be completely unaffected by a transformation, equivariance is more flexible. It says that a transformation applied to the input will also appear, in the same structured way, in the output. Formally, f is equivariant with respect to t if applying t before f gives the same result as applying f before t. The cleanest way to build intuition here is through a commutative diagram. Imagine a graph with colored nodes, each node carrying a feature vector. We have two paths. Path 1, first permute the node order with transformation t, producing t of x, then apply our function f to arrive at f of t of x, shown at the bottom right. Path 2, apply f first to get f of x, then apply the same permutation t to reach t of f of x. Equivariance says both paths produce the same result. F of t of x equals t of f of x. The function f and the transformation t are interchangeable in this diagram. Apply then permute is identical to permute then apply. Whichever road you take through the diagram, you always arrive at exactly the same place. This is why equivariant functions are so powerful for graphs and point clouds. Whatever permutation you apply to the input will show up, unchanged, in the output. The network structure and the symmetry are perfectly synchronized. Welcome to this. Let's make equivariance concrete with real-world examples. First, consider a protein structure prediction network. A protein is a three-dimensional arrangement of atoms. If you rotate the entire protein in 3D space, you're applying a rotation transformation t to the input. An equivariant model will produce an output that has been rotated by exactly the same rotation. Predicted atom coordinates, atomic forces, binding sites all rotate in lockstep with the input structure. This is the property molecular dynamics simulations need to be physically meaningful. Second example, a robotic arm. The arm operates in 3D space. If you rotate your entire frame of reference, an equivariant model's output rotates with it in exactly the same way. Whatever transformation you apply to the input, the output mirrors it faithfully. This leads to a key insight worth pausing on. What happens when the output of our function is just a single scalar, a real-valued prediction like energy or a classification score? A permutation or rotation of a scalar leaves it unchanged. So for scalar outputs, equivariance collapses directly to invariance. Invariance is simply a special case of equivariance where the output space is one-dimensional. Welcome to this. Now that we understand what equivariance and invariance are, the natural question is, why should we care? The answer comes down to two fundamental benefits. First, symmetry-constrained models have fewer free parameters to learn because they cannot encode representations that violate the known symmetry. This leads directly to better data efficiency. The NeurIPS paper by Batzner and colleagues, Nature Communications 2022 demonstrated this dramatically. Their equivariant model outperforms existing baselines with up to 3 orders of magnitude fewer training data points. This log-log plot from Bremer and colleagues, 2025, shows it clearly. The x-axis is training compute, the y-axis is prediction loss. The green equivariant line sits consistently below the blue-dashed baseline, lower error with far less data. The second benefit is robustness and out-of-distribution generalization. Because the symmetry is encoded into the architecture by construction, not learned from data, the model generalizes reliably to inputs never seen during training, as long as those inputs obey the same underlying symmetry. In short, if your data has a known symmetry, encoding it directly into the architecture is almost always worth it. You get more from less data, and far stronger generalization. Welcome to this. The foundations of this field were laid in a landmark paper by Bronstein, Bruna, Cohen, and Velikovic, Geometric Deep Learning, Grids, Groups, Graphs, Geodesics, and Gauges. The title is not accidental, those 5 G-words name the core domains the framework unifies. It gave CNNs, GNNs, and transformers a single symmetry-based blueprint and a common mathematical language. Around the same time, at NeurIPS 2020, Rishi Kondor and Taco Cohen ran a full tutorial on equivariant networks, a clear signal that the community recognized this as a major research direction worth a dedicated tutorial track. And since those foundational works, the field has moved fast. New modeling strategies have emerged for building equivariant architectures more efficiently. Entirely new problem areas have opened up, most notably neural parameter symmetries and weight space learning, where the symmetries live inside the model weights themselves. New theory has sharpened our understanding of what equivariant models can and cannot express. And ongoing empirical observations, insights, and open discussions continue to push the frontier forward. This tutorial sits right at the frontier of all four of these threads. By the end, you will have the tools to understand, implement, and reason about equivariant models, including the newest strategies that go well beyond the original geometric deep learning blueprint. Welcome to this. Before we dive into the math, let us step back and orient ourselves. This tutorial is structured in two parts. Part 1 covered the introduction and basics of symmetry invariance and equivariance and techniques for building equivariant models, with concrete examples. Part 2 goes deeper, neural parameter symmetries and other recent directions, theoretical results, and a broader discussion of the field. Throughout, we keep coming back to two key definitions. The first is invariance, f of g.x equals f of x. Applying a transformation to the input does not change the output. The second is equivariance, f of g.x equals g.f of x. The transformation propagates through the function. Keep both in mind, they are the core of everything we will see. A quick disclaimer, this tutorial covers wide ground, but the field is vast. Many excellent works lie beyond our scope. Welcome to this. In the last part, we talked about symmetry transformations. Now, a key insight. The transformations we care about almost always form a mathematical structure called a group. Formally, a group is a set G, together with a binary operation, a way to compose two elements satisfying four properties. First, associativity. The order of grouping does not matter. G compose H, then compose L, equals G compose H compose L. Second, identity. There is a unique element E that do nothing transformation such that composing anything with E leaves it unchanged. Third, inverses. Every element G has a unique reverse, G inverse. Applying G then G inverse or the reverse order brings you back to the identity element E. Fourth and finally, closure. Composing any two group elements gives you an element that is still inside the group. You cannot escape. Permutations of n elements form a group. Composing two permutations gives another permutation, and every permutation is reversible. Rotations in three-dimensional space, the group So of 3 also form a group. Rotating twice is still a rotation, and every rotation has an inverse rotation. And translations in space also form a group. Shift by V, then by W, and you arrive at V plus W. The inverse is simply the negative shift. So whenever we talk about symmetries in images, graphs, molecules, or point clouds, the underlying structure is always a group. This is why group theory is the language of geometric machine learning. Welcome to this. Group actions and representations informally. We build intuition first, the formal treatment comes later. A group action is a way for G to act on a set X. For each G in X, we get G.X back in X. For example, the permutation group Sn acts on indices 1 through n. A permutation sigma relabels each index, it maps I to sigma of I. Another example, invertible matrices, the group GL of n act on vectors in n-dimensional space by matrix multiplication, A.x equals x. Each row of a dot products with x to produce one output coordinate. So far, actions tell us how G transforms elements of X. But to compute with these actions, to write algorithms, train neural networks, we need them as explicit matrix operations. That is what group representations provide. A group representation maps each group element to a matrix, a linear stand-in for the action. For permutations of vectors, sigma.x equals p sigma times x, or p sigma is a permutation matrix encoding sigma. For rotations, g.x equals rho of g times x. The map row assigns a matrix to each group element. The crucial requirement, rho must respect composition, rho of gh must equal rho of g times rho of h. This is the homomorphism property. We now add one more concept, the orbit. The orbit of x under G is every point reachable from x by some group element. Formally, orb G of x is the set of all G.x. Think of rotating a vector, every rotation traces a circle. Welcome to this. Having established groups, group actions, and representations as our building blocks, we return to the central question: how can we get equivariant and invariant models? The first family uses off-the-shelf models, made equivariant through processing. 3 techniques: data augmentation, canonicalization, and group or frame averaging. The second family constructs equivariant models by design. Approaches include linear equivariant layers with parameter sharing or group convolution, invariant theory, and representation theory. Both families build on the mathematical language we just developed. Our series continues by exploring each approach in depth. Welcome to this. Data augmentation is the simplest approach to symmetry. Given a data point X, we add transformed copies G.X for various group elements G directly to the training data, then train as usual. The advantage is simplicity, no architectural changes, any model works. The limitation: augmentation does not guarantee invariance everywhere, only on the augmented training distribution. Despite this limitation, data augmentation is ubiquitous from image classification to molecular property prediction. Welcome to this. Another approach: learn an encoder F that maps all elements of an orbit to the same latent point. Inputs related by a group action X in G.X should get the same representation. Formally, f of G.X equals f of X. In contrastive learning, we train F to pull same orbit elements together and push different orbit elements apart. Each orbit collapses to one point but different orbits stay separated, preserving class structure. This is powerful. The network learns symmetry from data, without any hard-coded equivariance in the architecture. The price: we get invariance, not transformation tracking. Welcome to this. Now a more ambitious goal: instead of invariance, we want equivariance with a learnable linear map. We want f of X to equal T sub A applied to f of X. The question is, how do we parameterize T sub A? One approach: use a neural network. An MLP takes the transformation A and the representation f of X, and predicts what T sub A applied to f of X should be. The training loss minimizes the distance between f of X and MLP of a comma f of X. However, this approach has a fundamental problem: the MLP does not guarantee consistency with how transformations compose. Applying a sub 1 then a sub 2 should give the same result as applying their composition directly, but the MLP may not satisfy this. This inconsistency was identified by Dangovsky et al. In 2022, De Villers and Lafort in 2023, and Garrido et al. In 2023. Welcome to this. There is a cleaner parameterization. Instead of an unconstrained MLP, we restrict T sub A to be a rotation matrix. R sub A rotations automatically preserve composition, and they preserve inner products. The training loss changes too. Instead of Euclidean distance, we use an inner product loss, minimizing the expected discrepancy between inner products before and after the transformation. This loss is 0 precisely when T sub A is a rotation. When this loss reaches 0, something remarkable happens. Each T sub A is encoded as a rotation R sub A that preserves composition. In other words, T sub A equals R sub A equals rho of A. It is a group representation. And importantly, the input transformation it does not need to be a rotation itself. This result connects to Peter and Whale from 1927, and was applied in the learning setting by Shakaranava et al. In 2022 and Gupta et al. In 2023. Welcome to this tutorial on research. With the mathematical foundations in place, let us quickly recap the full toolkit: 2 broad families of approaches for getting equivariant or invariant models. The off-the-shelf family includes data augmentation, canonicalization, and group or frame averaging. The constructing family includes equivariant layers, invariant theory, and representation theory. In this section, we zoom in on canonicalization, the idea of mapping every input to a standardized orbit representative before applying the model. Welcome to this. There are 2 natural strategies for making a function f invariant. Canonicalization applies f exactly once to a standardized representative of the orbit. Symmetrization, or group averaging, applies f to every orbit element and averages the results. Welcome to this. Canonicalization is straightforward in principle. Instead of applying f directly to X, we first map X to a canonical representative of its orbit, a standardized form. All orbit elements share the same canonical form, so F becomes invariant. The classic example is sorting for permutation invariance. Take the vector 5, 3, 4. Sorting always gives 3, 4, 5 the canonical form. Apply F, say it computes x sub k minus x sub 1, giving 2. Now consider a different permutation, 4, 3, 5. It sorts to the same 3, 4, 5, so output is also 2. No matter the input permutation, the result is identical. This is permutation invariance. For permutation equivariance, we add one step. After applying F in canonical space, we invert the original sorting permutation to map the output back to the input's order. Different input permutations use different sort permutations, so inverting them produces outputs correctly related by that permutation equivariance is preserved. And canonicalization does not need to be handcrafted. It can be learned by a neural network, and recent work has shown this is effective in practice across multiple domains. Welcome to this. Canonicalization is not always easy to define. Some group actions such as rotations combined with permutations for point clouds do not have a simple canonical form. And when the input itself has symmetries, the canonical form can be ambiguous. The most fundamental challenge is continuity. We want canonicalization to be continuous. Close inputs should map to close canonical forms. Consider 5, 3, 3. Sorting gives 3, 3, 5. Perturb slightly, 5, 3.01, 3. Sorting gives 3, 3.01, 5. These are close. In this one-dimensional case, continuity holds. But this is a deceptively simple case. In one dimension, sorting is well behaved. Adding even a second row of values making the input a matrix of vectors breaks this continuity entirely. Welcome to this. Now we add a second row. Each input is a matrix of two stacked vectors. Matrix 1, top row 5, 3, 3 bottom row 1, 7, 8. Sorting columns by the top row gives 3, 3, 5 with the bottom row reordered to 7, 8, 1. Now perturb the top row, 5, 3.01, 3. Sorting now uses a different column order and the bottom row becomes 8, 7, 1. A tiny change in input caused the bottom row to jump. Continuity has broken. This is not a special case, it is unavoidable. No matter how we design the canonicalization, as soon as we have more than one vector in more than one dimension, some pair of close inputs will always map to far apart canonical forms. The same impossibility holds for SO, too. This theoretical limit was established by Dym et al. In 2024 and Zhang et al. In 2020. It motivates alternative approaches, particularly group averaging and frame averaging, which we turn to next. Welcome to this tutorial on recent development. The simplest way to symmetrize any neural network is group averaging, also called the Reynolds operator. The key insight is elegant: average the model's output over all transformations of the input. To make F invariant, we compute F bar of X equals 1 over the group size, times the sum over all group elements G of F applied to G inverse dot X. Here, F can be any generic neural network, it does not need to be equivariant itself. The averaging does all the symmetrization work. For equivariance, we add one more step. After applying F, we also apply G to the output before averaging. This ensures the averaged function transforms correctly when the input transforms. Equivariance is preserved by construction. Group averaging is simple and expressive. Yarotsky 2021 shows it universally approximates any invariant or equivariant function. The catch: summing over all G is expensive. For large or infinite groups, we must resort to approximations. Welcome to this. Let us look at a concrete example. Consider the symmetric group Sk, the group of all permutations of k elements. This has k factorial elements, which can be large, but the averaging formula is well defined. Genasi pooling instantiates this for sequences. Given inputs x1 through xk, we enumerate all k factorial ordering sigma in Sk. For each ordering, we pass the reordered sequence to F, then average the results. This is the Genasi pooling formula. The result is invariant to the input order. For k equals 3, S3 has 6 elements, 6 permutations. Suppose our input is A, B, C. We enumerate all 6 orderings, ABC, ACB, BA, BCA, CAB, CBA. We apply F to each ordering, sum the results, and divide by 6. The output is the same regardless of which order we originally presented A, B, and C. Beyond sequences, this applies to graph neural networks. Relational pooling applies Genasi pooling over node orderings, making message-passing networks more expressive. For large K factorial grows fast in practice, we sample a random subset as an approximation. Welcome to this tutorial on recent development. Our second example is SignNet. Eigenvectors have a fundamental sign ambiguity. If Vi is an eigenvector, then negative Vi is equally valid. We want any function of eigenvectors to satisfy f of Vi equals f of negative Vi. SignNet achieves this elegantly. Apply a shared learned network phi to Vi and to negative Vi, then add. Feed all these phi sums into a final learned network H and you have a sign invariant function. In practice, a graph comes with adjacency, node features, and Laplacian eigenvectors. SignNet processes the eigenvectors with the phi sum construction, then feeds the result into any prediction model, a GNN or transformer for downstream tasks. SignNet extends beyond graphs to neural fields on manifolds where eigenvectors of the Laplace-Beltrami operator define shape features. The sign invariant processing makes representations consistent across arbitrary eigen decompositions. Welcome to this tutorial. We've seen 2 extremes. Canonicalization picks a single representative, while group averaging sums over all of G. Frame averaging lives in between. We average only over a carefully chosen subset f of x inside G. Concretely, for invariance, we average f of tau inverse times x over all tau in the frame f of x. For equivariance, we apply tau to the output before averaging. Both mirror group averaging, but sum only over f of x far smaller than G. The key requirement is that the frame itself must be equivariant. If you transform the input x by G, the frame transforms by the same G. Without this, the average would not be invariant or equivariant, it would just be an arbitrary subset. This diagram shows, transforming first then computing the frame gives the same result as computing the frame first then transforming. Frame averaging hits a sweet spot, cheaper than full group averaging when the frame is small. Unlike canonicalization, it can yield a continuous function when the frame is equivariant, though continuity is not guaranteed in all cases. Crucially, it preserves the expressiveness of the base model. Welcome to this tutorial. Our concrete example is point clouds, like protein structures. The symmetry group is E3, rotations, reflections, and translations. A frame-averaged model must treat all orientations and positions of the same point cloud identically. To build a frame for point clouds, we use PCA, compute the covariance of X, extract eigenvectors V1 through Vd, and center at the centroid T. Each alpha I is +1 or -1, giving 2 to the D frame elements. Frame averaging then applies, average phi of X rotated and translated, over all frame elements. Each alpha I being +1 or -1 gives exactly 2 to the D sign flip frames. This sign flip structure directly mirrors the eigenvector sign ambiguity handled by SignNet. For proteins and antibodies, we use SE3 rotations and translations only, no reflections since molecular chirality matters. Frame averaging makes any backbone GNN or transformer equivariant to rigid body motions. Welcome to this tutorial. Frame averaging sounds like the best of both worlds. But there are fundamental limits. Theoretical results tell us when a finite, continuous, equivariant frame simply cannot exist. For the permutation group acting on n by d matrices with n and d both greater than 1, the only continuous equivariant frame is the full symmetric group Sn itself. There is no smaller finite frame that stays continuous. Similarly, for SO2, the rotation group on the plane, a continuous equivariant frame is generally not finite. You would need infinitely many rotations to stay continuous. The good news, weighted frames can help. Instead of equal weights, each frame element carries a learned weight W of tau and X. Smaller frames become possible with partial recovery of continuity. Welcome to this tutorial. Now let's put all 3 approaches on a single spectrum and compare them on cost and continuity. Starting with cost, canonization is cheap. It picks a single transformation. Frame averaging can be cheaper than full group averaging when the frame is small. Group averaging over the full group can be expensive or require approximations. On continuity, canonization is not continuous. A small change in input can jump to a different canonical form. Frame averaging still has continuity issues. Only group averaging is continuous by construction. All three approaches share important general advantages. First, they preserve the expressiveness of the base model, letting you reuse successful existing models and training methods. Second, they can easily combine symmetries. Third, they are easy to apply. The bottom line, symmetrization lets you take any existing non-equivariant model and make it equivariant, off the shelf. The right choice depends on your group, your budget, and your continuity needs. Welcome to this tutorial. We've now covered 3 ways to symmetrize any existing model: data augmentation, canonization, and group or frame averaging. All of these work off the shelf, with no changes to the underlying architecture. But there's a second family. Rather than symmetrizing an existing model, we can construct equivariant layers from scratch using parameter sharing, group convolution, invariant theory, and representation theory. This is what the next part of this tutorial explores. We've covered how to symmetrize existing models. Next, we'll see how to build equivariant layers from scratch. As a reminder, 2 core mechanisms that power all geometric neural networks: equivariance and invariance. First is the equivariant layer. Imagine passing a geometric structure, like a triangle, through a neural network to extract features. Equivariance means, if the input is transformed, for example, rotated by an angle, the output will rotate in the exact same way. The geometric structure is perfectly preserved. The second concept is the invariant layer, often used in pooling. Here, features are aggregated into a single global value. Invariance means, no matter how you rotate, flip, or transform the input, the output remains exactly the same. The network has distilled the core information. So what is the big picture? In practice, architectures like CNNs or GNNs chain multiple equivariant layers to process deep spatial structures. Finally, they use an invariant layer to make a prediction that is independent of the viewpoint. Models are usually divided into 2 clear parts: geometric feature extraction and aggregation. Let's look at a concrete example using deep sets. We have an equivariant layer applying a multiply by 2 function to each input element. 1, 2, and 3 become 2, 4, and 6. If we swap the positions of the input elements, their positions in the output automatically swap as well. This is permutation equivariance. Next, we pass these values through an invariant layer using some pooling, getting a total of 12. Now, even if you shuffle the input elements 1,000 more times, the final sum will always be 12. Our prediction is completely invariant to the order. Now, let's look at the generic construction of a geometric neural network. As we discussed, these models stack multiple equivariant layers to process structural information, followed by an invariant pooling layer at the end. There are many types of equivariant layers. Some common examples include linear equivariant layers with nonlinearities, group convolutions, or equivariant polynomials. These are the building blocks of famous architectures like CNNs, graph neural networks, and deep sets. Let's focus on the most fundamental one, the linear equivariant layer, and its core principle, parameter sharing. A standard linear layer applies a weight matrix W to the input X, followed by an activation function. To make this layer equivariant to a specific symmetry, we must force a specific structure onto the weight matrix W. This mathematically results in parameter sharing. How do we define this mathematical constraint? It can be written as an elegant equation. W times P underscore G times X equals P underscore G times W times X. Here, X is the input data. W is the learnable weight matrix. And P underscore G is the symmetry transformation matrix, representing actions like rotating, flipping, or permuting. Let's visualize this with an example. We start with an input grid X. First, we apply a geometric transformation, such as a 90-degree rotation. This gives us p_g times x. Then, we apply the neural network layer W to extract features. The result is W applied to p_g of x. This brings us to a fundamental concept, the commutative diagram. Path number 1, we first transform the input with p_g, and then apply the neural network W. This gives us the left side of our equation. Path number 2, we apply the neural network W first, and then apply the geometric transformation p_g to the feature maps. For a layer to be equivariant, both paths must commute. Meaning, it doesn't matter which path you take, you must end up with the exact same result. Now, let's derive the constraint for the weight matrix, specifically for the permutation group. Here, p_tau is the permutation matrix that shuffles rows and columns, and W is our parameter matrix. Starting from the original commutative equation, we drop the x. Since permutation matrices are orthogonal, their inverse is simply their transpose. By multiplying both sides by the transpose from the right, we arrive at the final condition. The matrix W must be invariant to conjugation by the permutation matrix. What does this mathematical constraint actually mean in practice? It leads directly to parameter sharing. It says, if a symmetry transformation tau maps the index pair I, j to a new pair k, l. Consider a dense weight matrix W. We select an element at position I, j. If the geometric transformation maps this position to k, l, then the element at k, l must share the exact same weight value. This rule applies across the entire matrix. Symmetric positions are forced to share parameters, greatly reducing the model's complexity. Let's view a classic example, 1D cyclic translation, which is the foundation of convolutions. We begin with a base weight vector containing 4 unique parameters. If the data shifts, the neural network weights must shift cyclically as well to maintain equivariance. We duplicate and shift the vector step by step. This stacked operation forms a circulant matrix. Notice how the same parameters align perfectly along the diagonals. This is the visual essence of parameter sharing in CNNs. Let's build our intuition on the one-dimensional cyclic shift. Imagine a simple one-dimensional vector with 4 elements, x1 through x4. A cyclic shift operation moves each element to the right, or the last element wraps around back to the beginning. Mathematically, the new index is calculated using addition modulo n. How does this dictate the structure of our weight matrix W? To be compatible with the input shift, the rows of the matrix must also shift cyclically. This results in a circulant matrix. We now only need exactly n parameters instead of n squared. Notice how the identical parameters share the exact same diagonal stripes. Step 3. Let's see how this translates to the mechanism of a 1D convolutional neural network. We start with our input sequence and apply circular padding by copying the initial elements to the end. Then, we introduce a learnable filter, or kernel, that will slide across the input. As the filter slides step by step, it computes the output. When it reaches the end, the circular padding allows it to seamlessly wrap around, just like our cyclic shift. This sliding window with wraparound is mathematically identical to our circulant matrix. Therefore, 1D CNNs with circular padding are naturally translation equivariant. Next, let's explore example number 2, all permutations of a set, and understand permutation symmetry. Consider an input consisting of a set of vectors, such as a 3D point cloud representing an object. We can represent this point cloud as an n by 3 coordinate matrix. Let's track a few specific points. Notice that if we permute the rows, meaning we change the order in which the points are stored in memory, the physical shape of the object remains completely unchanged. In mathematics, a collection like this is called a set. And a fundamental property of a set is that the order of its elements does not matter. If we perform a permutation, for example, swapping the first and third elements, or swapping the second and fourth elements, The structural meaning of the set is perfectly preserved. Because all elements in a set are structurally equal, an element can only distinguish between two things, itself, and all the other elements interacting with it. Let's formalize this with mathematical notation. A permutation can be represented by a permutation matrix, denoted as p tau. When we multiply this matrix by our data vector x, let's see what happens step by step. The matrix multiplication takes a row of p tau and multiplies it by the column of x. A number 1 at column j simply picks out the element xj and places it in the output. If we swap the rows of the permutation matrix, the corresponding output elements swap perfectly along with it. Now, how does this restrict our learnable weight matrix W? To remain equivariant to permutations, W can only have two unique parameters. The diagonal parameter, alpha, represents an element's interaction with itself. The off-diagonal parameter, beta, represents its identical interaction with all other elements in the set. This mathematical restriction leads directly to the basis elements of famous architectures like DeepSets and PointNet. The operation elegantly simplifies to a linear combination of the element itself and the sum over all other elements in the set. Let's discuss the consequences and extensions of parameter sharing. First, let's reflect on the nature of colors, also known as basis elements. As we've seen, each value in the weight matrix can be represented as a linear combination of these basis parameters. The number of unique colors, or the basis size, dictates the exact number of learnable parameters in the neural network layer. Second, we can extend this mathematical framework to graph neural networks, specifically invariant graph networks. Here, the input is a graph adjacency matrix. The symmetry we care about is the permutation of graph nodes. If we swap two nodes, the underlying graph remains structurally identical. However, analyzing the weight matrix for graphs reveals that it requires exactly 15 different basis elements to represent all symmetric relationships between node pairs. Finally, let's look at extensibility and limitations. This mathematical framework can be generalized to higher-order graph neural networks using tensors. It can also be applied to complex sets of symmetric elements. But there are limitations. Solving for these basis elements is not always computationally feasible for complex symmetries, and linear layers alone might lack the expressivity needed for advanced geometric tasks. Let's dive into group convolution. To understand it, we must first look at the regular 2D convolution we know and love. Here is the standard convolution equation, applying a filter psi over an image f. Let's visualize this on a pixel grid. Let x be the current center position of our filter. Let y be a neighboring pixel we are scanning. The vector y minus x gives us the exact relative coordinates of y with respect to x. The summation sign forces the point y to scan through all surrounding cells within the local filter region. The crucial insight here is translation equivariance. The filter weights depend strictly on the relative vector y minus x, not their absolute positions. Now, let's generalize this to an abstract group G. Notice how the subtraction y minus x is replaced by the group operation G inverse H. Imagine our group space represents rotations. Instead of position x, G represents our current filter's rotational state. And H represents the state we are currently scanning. To find the relative distance, analogous to vector subtraction, we must mathematically rewind the space by applying the inverse of G. Watch as we rotate the entire system back by G inverse. The new relative position is G inverse H, perfectly mirroring our 2D vector subtraction in the group space. This brings us to group equivariant CNNs. By using this generalized convolution, neural networks guarantee equivariance to complex symmetries like rotations and reflections. This beautiful and foundational concept was first introduced by Taco Cohen and Max Welling in their landmark 2016 paper. Let's explore invariant polynomials. Step 1, the core idea. Instead of relying solely on linear layers, we can approximate complex functions using invariant polynomials. The symmetry constraints are exactly the same as before. A polynomial function can be either invariant or equivariant to a group transformation. Using scalars. Any invariant polynomial can be expressed cleanly as a function of basic scalar quantities. Let's look at a 2D space with two vectors, x1 and x2. Notice the table. As we continuously rotate the system, the individual coordinate values change dramatically. However, the dot product and the squared distance remain completely static. They are invariant scalars. Universality. It is obvious that these scalars are invariant under rotation. But the truly amazing part is their mathematical universality. This means any generic invariant polynomial can be decomposed and written simply as a function of these basic scalar quantities, like the dot product and distance. Let's look at some concrete geometric examples. First, invariance under the orthogonal group, which includes rotations and reflections. Consider a point cloud in a 2D space, centered around an origin O. An invariant function can be constructed using the inner products of these vectors. As we know, the inner product depends strictly on the lengths of the vectors and the angle between them. Let's observe a real-time dashboard of these values. When we rotate the entire point cloud around the origin, notice that while the absolute coordinates change continuously, the length and the angle remain completely fixed. Because the inner products are unchanged, the output of the function f remains perfectly invariant to the rotation. Example 2, equivariance under the orthogonal group. Here, the output is a linear combination of the original vectors, scaled by invariant weights. Because the weights are invariant scalars, when the input space rotates, the output vector is algebraically forced to rotate along with it. Let's observe this behavior. We have our invariant weights, and the angle of our output vector. As we rotate the point cloud, the angle of the output vector changes by the exact same amount. This perfectly demonstrates equivariance. The output rotates perfectly in sync with the input. Example 3, invariance to translation. To achieve this, we can select one point, say v1, as the local origin, and represent all other points as relative vectors. Let's track the absolute coordinates of v1 and v2, and their relative vector distance. As we translate the entire point cloud across the space, the absolute coordinates constantly change, but the relative distance between them remains completely constant. Because the relative vectors are unchanged, the output function is completely invariant to translation. To summarize these fundamental principles. Orthogonal invariance is built using inner products. Orthogonal equivariance is achieved via linear combinations of the original vectors. And translation invariance uses relative coordinates. These mathematical constraints guarantee that our geometric models can reliably recognize structures, no matter how the data is transformed in space. Let's explore equivariant graph neural networks. In an EGNN, each node processes two completely distinct streams of information. First, we have node features, denoted as HI, like mass or charge. These are invariant. They don't change when the molecule rotates. Second, we have the spatial coordinates xi. These are equivariant, meaning they rotate in sync with the physical system. Let's dissect the EGNN coordinate update formula. The update has two parts. A relative vector provides direction, and an invariant neural network computes the scalar force magnitude. We can visualize this message passing as physical forces acting on node I. First, we define the interaction lines along the relative vectors. The network computes the force magnitude, either pushing or pulling the node. Aggregating these forces gives us the final displacement for the coordinate update. This works because as the graph rotates, relative distances remain static, while the force vectors naturally rotate in sync. Let's apply these geometric concepts to a real-world application, protein generation models. Stage 1 is the macro generation process. We start with a collapsed, noisy polymer chain representing pure unstructured data. Through a reverse diffusion process, the model gradually denoises this blob to form the stable 3D backbone of a protein. Finally, a specialized design network completes the structure by generating the specific amino acid side chains. Stage 2, let's zoom into a single microstep of this denoising process using an equivariant GNN. At step T, the noisy structure XT is passed through a GNN which predicts noise vectors. These are refined by an equivariance solver to estimate the original structure. This central core leverages geometric deep learning to ensure the denoising is robust to spatial orientation. Stage 3, understanding how we guide protein generation using specific conditions. The goal is to generate a protein X that satisfies requirement Y. This is a sum of the prior model and the conditioner. The prior handles natural valid protein structures, while the conditioner ensures it meets our design constraints. Conditions can include symmetry, specific substructures, or global shape requirements. Let's begin with our primary object, a standard multi-layer perceptron. Here, every single connection weight is completely independent. With this dense web of unique parameters, signals can flow freely, allowing the model to approximate virtually any complex function. But what happens when we demand geometric structure? Let's paint the top neuron red and the bottom neuron blue. Equivariance strictly dictates a structural law. If we swap the positions of these input elements, the internal transformations must commute the geometry perfectly, forcing the corresponding outputs to swap in the exact same manner. To maintain this flawless symmetry, we must force the network weights to satisfy the equivariant algebraic constraint. By Clebsch-Gordon decomposition, this constraint instantly strips away the matrix's freedom. Look at the network, all cross-connections vanish, and the remaining parameters are locked into a single scalar multiplier. Instead of processing individual elements separately, we duplicate the input vector into a row and a column representation. Watch how the tensor product unfolds. As the row values multiply across the column values, their pairwise interactions populate a new 2D feature matrix. From this rich multi-dimensional space, independent parameters explode back into existence. We have restored complete universality while fully honoring our symmetry rules. Next to tensor methods part 2. Let's briefly recap how tensors expand our feature space. We start with a standard 1D feature vector X. Taking the tensor product squares the space into a 2D matrix, capturing pairwise interactions. Repeating this process k times creates a massive, high-dimensional tensor cube. When we feed these high-dimensional tensors into an equivariant multi-layer perceptron, the network preserves symmetry perfectly. Notice how rotating the input point cloud dictates a perfectly synchronized rotation in the output function. Furthermore, this method guarantees universality. We can decompose the input space into fundamental, orthogonal basis features. By feeding enough of these tensor components into the network, it can mathematically approximate literally any continuous equivariant function. Theoretically, as the tensor order k approaches infinity, the parameter space becomes dense enough to model anything. But there's a catch. The dimension of this tensor space scales exponentially, as d to the power of k. For k equals 1, it's lightweight. For k equals 2, the dimension squares. At k equals 4, it explodes. A large K creates a massive, computational nightmare filled with redundant symmetries. The mathematical solution is to decompose this giant matrix into irreducible, independent blocks using Clebsch-Gordan decomposition. We project the tensor space into a direct sum of these smaller, orthogonal representations. Now, the data is incredibly compact, redundancy-free, and computationally manageable. Finally, let's address a foundational dichotomy in geometric deep learning: continuous versus finite groups. For continuous symmetry groups, like 3D rotations, the transformations are buttery smooth. We can elegantly decompose this continuous space using well-understood analytical functions, known as spherical harmonics. In stark contrast, arbitrary finite groups operate through rigid, discrete jumps. There is no smooth transition, only sudden permutations. Because of this jumpy nature, creating a generalized mathematical decomposition for finite groups requires entirely different, often combinatorial algebraic strategies. We further explore how geometric machine learning is revolutionizing our understanding of atomistic systems. Traditionally, we represent molecules using 2D chemical structures. However, for machine learning, it is much more powerful to view them as 3D graphs of atoms, where nodes or atoms and edges represent their interactions. Why can't we just use a standard neural network, like an MLP, to process this data? At first, the MLP simply memorizes the specific spatial layout of the training data. But what happens if we shift the molecule? The coordinates have changed completely. The MLP fails to recognize it as the same molecule. What if we rotate it? Physically it's identical, but mathematically the input matrix is rotated. The MLP fails again. And what if we simply swap the order we feed the atoms into the network? The MLP treats permutation as completely different data. This is why we need geometric machine learning. By replacing the dense MLP with an equivariant graph neural network, we bake physical symmetries directly into the internal architecture. A graph neural network operates by passing messages between connected atoms, inherently understanding the underlying structure. When the molecule is translated through space, the relative distance vectors between atoms remain completely unchanged. The GNN naturally ignores absolute coordinates. Success! Crucially, when the input molecule is rotated, the model's geometric features adapt automatically, rotating the output target in perfect synchronization. Equivariance in action. Finally, if we arbitrarily swap the index labels of the atoms in our data array, the message passing routes are mathematically identical. The network is fundamentally order-independent. Ultimately, our goal is to advance atomistic science. We often need to map an atomistic system to its physical properties, like energy and forces. Traditional scientific computing methods do this, but they are notoriously slow and expensive. This loop is critical for fields like medicine design. Geometric machine learning acts as a powerful accelerator, drastically speeding up these computations while preserving strict physical laws. In atomistic machine learning, our primary goal is to predict the potential energy of a molecule and the forces acting on each atom. Physics tells us that energy E is a scalar value that is strictly invariant to 3D rotations. And the force F is a vector field, defined exactly as the negative gradient of the energy with respect to atomic coordinates x. Let's see what happens if we rotate the molecule by a matrix R. By substituting our x into the gradient, the multivariable chain rule naturally pulls the rotation matrix R outside of the gradient operator. This elegantly proves that modeling an invariant energy automatically guarantees a perfectly equivariant force field via backpropagation. Visually, these autograd force vectors are attached to each atom. If we rotate the input geometry, the force vectors gracefully rotate in absolute synchrony. That is the essence of equivariance. To maximize this capability, modern architectures like the equiformer replace local message passing with a global attention mechanism. Every atom is directly connected to every other atom. By modulating these connections with spherical harmonics, the model captures complex 3D structures flawlessly. Let's build an articulated robot arm to see exactly how equivariance ties the math to physical motion. First, the optimal policy maps the current state to a specific sequence of joint angles. Now, let's return the arm to its resting position. What happens if the target state undergoes a 90-degree rotational transformation? Thanks to the equivariant architecture, the policy doesn't need to learn a new path from scratch. It perfectly commutes the geometry. The base joint simply absorbs the 90-degree shift, while the relative elbow angle remains completely unchanged. Imagine a pencil balancing perfectly upright on a table. This system has perfect rotational symmetry. You can look at it from any angle, and the state x remains identical. If we ask an equivariant neural network to predict how this pencil will fall, the math traps it completely. Take any transformation g that keeps the pencil upright. Applying g to the predicted output y gives g times f of x. Because the network is strictly equivariant, this is equal to f of g times x. And since g leaves x unchanged, the output collapses back to just f of x, which is exactly y. This proves that any symmetry belonging to the input must be violently inherited by the output. The network cannot break symmetry. In physical reality, the pencil falls in one random direction. But the AI is forbidden to pick a side. Thus, it predicts the pencil falling in all directions simultaneously, forming a blurred circle, or just standing still forever. To escape this trap, researchers use weight perturbation, injecting a tiny drop of random noise to shatter the perfect balance, allowing the physics to finally collapse into reality. Hard-coding symmetries beforehand can limit the power of foundation models. Instead, models should flexibly encode them and adapt based on the data context. For example, when encountering data type A, the model automatically selects horizontal flip and color change symmetries. But when encountering data type B, it activates 3D rotational symmetry. Another elegant mathematical approach is to provide the model with a special input, called vector v, to break the general symmetry. Look at this condition: the transformation g only retains its equivariance if it preserves vector v. This means, if we rotate the entire system around the axis of v, vector v remains unchanged. This subgroup symmetry is accepted. However, if we rotate along a different axis that tilts vector v, the equivariance symmetry is immediately broken for that rotation direction. Finally, a major question arises: what if we have absolutely no prior knowledge of the symmetries in the physical system or dataset? The answer is simple: let the neural network discover and learn them on its own. We can achieve this by forcing the model to learn data augmentations, automatically share weights, or by probing a trained neural network. When we train a neural network, we usually think of a unique set of parameters leading to a unique function. But in reality, neural networks possess massive parameter symmetries. This means two entirely different arrangements of weights, theta and g times theta, can express the exact same mathematical function. Consider a standard multi-layer perceptron. If we swap the positions of these two internal hidden neurons, we must simultaneously permute the rows of the incoming weight matrix W1 and the columns of the outgoing matrix W2. Moreover, if the network uses homogeneous activation functions, we discover scale invariance. By scaling up the output weights by a factor of alpha, and simultaneously scaling down the input weights by the exact inverse of alpha, the mathematical effect perfectly cancels out. The internal geometry shifts entirely, yet the final network output is absolutely invariant. Another fascinating symmetry occurs inside matrix products, widely seen in low-rank adaptations, or LoRAS, and attention blocks. We can inject any arbitrary invertible matrix R and its inverse right into the bottleneck layer. If we group R with U, and are inverse with V-transpose, the absolute weight parameter values shift drastically, yet their collective dot product remains entirely unchanged. Whether it is scaling factors, head permutations in transformers, or orthogonal groups in RMS norm, parameter symmetries define the complex geometry of our loss landscapes. Symmetries in neural networks can be categorized into two main types. The first is functional symmetry, where transforming the parameters results in the exact same mathematical output for any input. However, a much broader category is loss symmetry. Here, the internal functions might behave differently, but they ultimately yield the exact same objective loss value. In the vast optimization landscape, this means there are multiple distinct parameter configurations that sit at the exact same altitude. Point theta and its symmetric counterpart g theta are physically distant, yet perfectly equivalent in terms of performance. A classic example of loss symmetry is contrastive learning. The network outputs embedding vectors for different inputs. If a symmetry operation, like a rotation, alters both output vectors simultaneously, the individual outputs change, breaking functional symmetry. But the angle and inner product between them remain exactly the same. Thus, the loss is perfectly symmetric. So, keep in mind that in complex real-world models, these symmetries might only hold over the entire data distribution, rather than for every single point. The core equation of parameter symmetry states that, if theta is a local minimum providing an optimal loss, then applying a symmetry transformation G results in a new state that preserves the exact same loss value. Observe this smooth three-dimensional loss landscape. At the base of this quiet valley, we find two local minima, theta A and theta B, highlighted here. Thanks to continuous symmetry, these points are actually connected by a path of invariant low loss. This is the phenomenon of mode connectivity. Looking from above, we scale the background valley map so that the distance between the two solutions perfectly matches our new two-dimensional axes. If we take a straight-line path between the two models without alignment, the interpolation hits a massive loss barrier due to structural misalignment. However, by using a permutation matrix pi to align the neuron ordering, the barrier vanishes, revealing a flat and safe path through parameter space. Let's visualize why learning dynamics differ so drastically. Here is a loss landscape where the curvature is extremely steep in one direction and very flat in the other. Take point theta. It sits on a steep slope. If we apply standard gradient descent, the high curvature causes severe oscillations, slowing down convergence. But its symmetric counterpart, g theta, lies on the exact same contour line in a flatter region. From here, the optimization trajectory is perfectly smooth and direct. This visually proves why actively searching for symmetric transformations, or using invariant algorithms like PathSGD, can dramatically accelerate deep learning. Another profound implication is the emergence of conserved quantities. Much like energy in physics, certain properties of the network remain constant during optimization. Consider the weight matrices of two consecutive layers. As the network trains, their individual magnitudes might grow substantially. However, because of the underlying parameter symmetries, the difference between them is locked. This invariant controls the optimization trajectory, preventing the layers from becoming severely imbalanced. We are now entering a fascinating paradigm shift in machine learning, treating neural networks themselves as data. A traditional network processes data layer by layer. But imagine taking the entire weight space of this trained network and collapsing it into a single, high-dimensional point. We then feed this massive weight vector into a higher-level architecture called a metanetwork. Notice how its internal states process entire grids of parameters. Its goal is to deeply analyze and edit the fundamental symmetries of these models. As the functional processes the model, it eventually outputs a highly optimized, structurally edited version of the original network. A perfect example is implicit neural representations, like NeurIPS. instead of storing 3D scenes as pixels or voxels. We train a tiny, unique neural network to map spatial coordinates and viewing rays directly to color and density. Multiply this by thousands of 3D objects, and your dataset is no longer just images. It is a dataset composed entirely of neural networks. And this concept extends far beyond 3D scenes. Today, platforms like Hugging Face host over 2 million open-source models. From computer vision architectures to massive language models, they form an evolving, deeply interconnected population of weight spaces. To build algorithms that can automatically search, merge, or generate new models within this vast universe, we must first decipher the mathematical symmetries hidden inside them. Why should we treat neural networks as data? What is the practical use of a metanetwork? Let's explore 3 revolutionary applications. First, predicting model performance. Normally, evaluating a model requires running millions of test images through its layers. Instead, a metanetwork can simply ingest the model's weight matrix, analyze its structural geometry, and instantly predict its accuracy. This bypasses the data pipeline entirely, making evaluation up to 50,000 times faster. Second, we can directly edit networks. A metanetwork can ingest a dense, heavy model, intelligently manipulate its internal weight space, and output a structurally pruned weight matrix. This instantly generates a brand new, highly compressed, and efficient model without any retraining. Perfect for on-device deployment. Finally, as the open-source model population explodes, we desperately need model forensics. By ingesting an unknown model from the internet, the metanetwork analyzes the structural fingerprint of its weights. It can decode this fingerprint to answer critical questions. Was it trained on copyrighted data? Is it safe? Does it carry hidden biases? Ultimately, weight space learning and metanetworks turn the chaotic, wild jungle of millions of models into a structured, searchable, and editable atlas. According to Navon et al., deep weight space networks structure parameters into distinct blocks to preserve permutation equivariance. When neurons in the hidden layers are permuted, the equivariance constraint forces the corresponding rows and columns in the weight block matrices to swap simultaneously. To scale up, neural functional transformers represent entire weight matrices as structured tokens, treating layers as sequence elements. Each token undergoes an equivariant projection, spinning out distinct query, key, and value weightspace representations. Now observe the matrix multiplication. The rows of query interact directly with the columns of key transpose. As they scan across the layers, their inner products intersect to map out the raw attention coefficients cell by cell. Finally, a row-wise softmax normalization passes through, smoothly scaling the weights into a fluid global activation map. But what if we aren't just dealing with fixed MLPs? Consider a standard, structurally rigid model like architecture A. Now contrast it with architecture B, featuring unpredictable layer widths and non-sequential skip connections. Traditional weight space networks completely fail here, because they expect fixed matrix shapes and cannot handle irregular topologies. This is where graph metanetworks introduce a revolutionary shift. Instead of forcing weights into rigid tensor blocks, every model is unified into a single graph representation. In this unified parameter graph, the original neurons themselves act as the vertices, and the weight values reside directly as attributes on the connecting edges. Because graph neural networks are inherently agnostic to size and layer boundaries, a single metamodel can now compute predictions across any arbitrary topology. Watch how messages flow. Node features are aggregated along the boundaries of the weights, creating structural awareness across the entire network architecture. By learning directly on this parameter graph metanetworks successfully unlock deep structural understanding across completely diverse model universes. To conclude, we must ask the critical question: does all this mathematical equivariance actually help in practice? Recent benchmarks on LoRa metanetworks reveal a stark contrast. Naive architectures that ignore parameter symmetries suffer from poor generalization accuracy. Worse, when scaling up to massive models like Llama, naive configurations completely run out of memory, collapsing entirely. In contrast, symmetry-aware methods like GLNet maintain absolute stability, achieving a near-perfect R-squared score of 0.998 while remaining highly efficient. Yet, as we look to the horizon, several profound questions remain open for the scientific community. First, how do we scale these meta-networks to process foundational models containing hundreds of billions of parameters? Second, how do we formalize strict mathematical rules to determine exactly when to enforce permutation invariance versus full layers equivariance? And finally, how can we leverage these geometric properties to seamlessly navigate, parse, and exploit the massive, interconnected model atlas of the future? Unlocking these hidden parameter symmetries will not only protect model security, but fundamentally reshape how humanity understands deep neural functions. We now move to one of the most exciting recent developments in geometric machine learning, the connection between expander graphs and symmetry. This section will show how ideas from combinatorics and group theory can make working with large symmetry groups computationally feasible. Let's start with the core problem. In many machine learning tasks, we need our models to be invariant or equivariant under a group of symmetries. Consider the permutation group SD, the group of all possible ways to reorder D elements. This is a finite group, but it is enormous. For example, when D equals just 50, the size of SD, that is, 50 factorial, is approximately 3 times 10 to the power of 64. To put that in perspective, this number is way bigger than the total number of atoms in the entire Earth, which is estimated at around 10 to the power of 50. Now recall the technique of group averaging. To make any function f invariant, we compute the average of f over all group elements. Specifically, f bar of x equals 1 over the size of G, times the sum of f of G inverse dot x, for every G in G. The key issue is that sum. When the group has 3 times 10 to the 64 elements, summing over every single one of them is completely impractical. Even the fastest computer could never finish. So here is the key question: can we find a small subset of a large finite group that retains enough of the group's structure for geometric ML, like data augmentation, averaging, and optimization? To answer this question, we turn to a classical concept from group theory, the generating set. A subset S of a group G is called a generating set if every element of G can be written as a product of elements from S. Let's see a concrete example. Take the permutation group S5. Our generating set S consists of adjacent transpositions, swap 1 and 2, swap 2 and 3, swap 3 and 4, and swap 4 and 5. Watch how we compose these simple swaps. Starting from 1 2 3 4 5, swapping positions 2 and 3 gives 1 3 2 4 5. Then swapping positions 1 and 2 gives 3 1 2 4 5. Just two generators, composed, already produce a new permutation. This has a powerful implication: if a function f star is invariant under every element of S, then it is automatically invariant under the entire group G. So instead of checking invariance over all of G, we only need to enforce it on the much smaller set S. But here is the catch: finding a minimum size generating set is NP hard in general. However, for SD, adjacent transpositions give us a generating set of size only D-1. Even though finding the exact minimum generating set is NP hard, we can still ask, what is the smallest possible size? A classical theorem gives a beautiful answer. For any finite group G, there exists a generating set with at most log base 2 of the order of G elements. This is an exponential saving. The group has G elements, but we only need about log G generators. For S50, where the group has 3 times 10 to the 64 elements, log base 2 of that is roughly 215. Just 215 elements can generate all 3 times 10 to the 64 permutations. However, there is a significant limitation: the proof is non-constructive. It tells us the small set exists, but gives no algorithm to find one. So the practical question becomes, can we find generating sets of size order log G in polynomial time? The answer is yes, using randomness. Here is the elegant solution. Instead of carefully constructing a generating set, we simply pick elements at random. The Alone-Reutemann theorem states, a randomly chosen subset S, with size proportional to log of the group size, is a generating set with high probability. More precisely, the size of S is about 2.67 times log G. This grows only logarithmically, an enormous saving. But this result tells us something even deeper. The Cayley graph built from this random generating set is an expander graph. In a Cayley graph, each node represents one group element. Think of it as a state of your data. Each edge corresponds to applying one generator from S. Now watch what happens when we do a breadth-first search. Starting from one node, level 1 reaches a few neighbors. Level 2 explodes outward. And by level 3, nearly the entire graph is covered. This exponential expansion is exactly the expander property. A short random walk on this graph can sample from the entire group efficiently. Now that we understand expander graphs and random generating sets, let's explore how these tools are actually applied in geometric machine learning. We will cover three major applications: data augmentation, approximate group averaging, and learning with exact invariances in polynomial time. A fundamental question in geometric machine learning is, can we learn an exactly invariant function efficiently? In Sobolev regression, learning with invariances is equivalent to solving a constrained optimization problem. The optimization takes the form, argmin over theta of L of theta plus eta times the squared norm of theta, subject to the constraint that rho of g times theta equals theta for all g in G. This is convex, which is good. But the constraint must hold for every element G in the entire group G, which can be astronomically large. The crucial observation, since rho is a group representation, meaning rho of GH equals rho of G times rho of H, we can replace the full group constraint with a constraint over just a generating set S. Same objective, but now subject only to rho of G theta equals theta for G in S. This replacement is lossless. The theorem from ICML 2025 states, one can find an exactly invariant estimator in time big O of log of G cubed. The first application is data augmentation. Normally we augment by applying all G in G to each data point. But full augmentation is prohibitive. For SD, the group has D factorial elements. Can a small subset S achieve the same statistical benefits? In classical density estimation using kernel methods, the answer is yes. The theorem proves, only O of log G random elements suffice for the full statistical gain. For SD, group size is about exp of d log d, but only O of d log d random augmentations are needed. An exponential improvement. The second application, approximate group averaging. We replace the full average over G with a partial average over S. The full average, sum over all G in G, is replaced by sum over just G in S. The key question, how large must S be? We need a uniform bound because F changes during training. The theorem gives, the worst case error is at most O of log G, divided by S. Error shrinks as S grows. The proof requires Fourier analysis on groups. Classical large deviation theory is insufficient here. Let's see a concrete experiment. Task: predict absolute value using a 3-layer ReLU net. The sign flip group has 2 to the 20 elements, about 1 million. The left plot shows test loss versus number of random sign flips used. Notice how loss drops sharply and plateaus around test equals 32. The right plot shows loss over training epochs. Orange, using only 32 flips, closely tracks the blue full group baseline across all epochs. Key takeaway, just 32 elements from a group of 1 million gives excellent approximation, with a single random draw. Now a remarkable negative result. What if we demand exact equality instead of just approximation? The condition, the full group average must exactly equal a weighted partial average, for all functions in a given class F. The theorem proves an exponential separation. For polynomial function spaces, exact symmetry via averaging requires a subset of size linear in the group essentially as hard as using the full group. But approximate symmetry only needs logarithmic size. The gap between them is exponential. The three-part corollary, exact symmetry is hard, needing linear complexity. Approximate symmetry is easy, needing only log. And crucially, the full statistical benefit is also achievable with log complexity. The punchline: you lose almost nothing by relaxing from exact to approximate symmetry, but you gain an exponential speedup. Let's summarize. Expander graphs and random Cayley graphs provide powerful tools directly relevant to machine learning. The key message: random subsets of size O of log G are almost as good as the full group, and this is provably tight. The techniques involve Fourier analysis on groups, expander graph theory, and optimization under symmetry constraints. Here are the key references for further reading. We now move to the second set of recent results, focusing on symmetry validation, specifically, testing whether a data distribution respects a given group symmetry. Given IID data drawn from a distribution mu, we want to decide whether mu is invariant under a group, or not invariant. Consider 2D rotational invariance as an example. A non-invariant distribution looks elliptical, while an invariant one forms a perfect ring. Applications include testing exchangeability, verifying symmetry assumptions in geometric machine learning, such as whether MRI images are truly rotationally symmetric, detecting subtle asymmetries that could bias models, and improving robustness and interpretability. Under the null hypothesis H0, the distribution mu is invariant, mu equals g.mu for all g in G. For example, if G is the group of 2D rotations, invariance of the density F means F depends only on the norm of X. Specifically, the vector x, y has the exact same distribution when multiplied by the 2D rotation matrix, consisting of cosine theta and negative sine theta in the first row, and sine theta and cosine theta in the second row, for any angle theta from 0 to 2 pi. Under the alternative hypothesis H1, mu is not invariant. There exists some g in G such that the divergence d between g.mu and mu is at least epsilon. Here d is a probability pseudometric satisfying the triangle inequality. Examples include optimal transport, kernel MMD, total variation, LP distance, Hellinger, and neural network features. We assume d is itself invariant under group actions. So the goal is a decision: either conclude mu is invariant, or certify it is not by finding a specific g in G that violates the symmetry. Even with infinite data, finding the worst-case g in G can be computationally challenging. There exists a setting where this arg subproblem is NP-hard. The proof reduces from a variant of the traveling salesman problem. But randomness can help. A key theorem shows that the expected divergence over a random G is always within a factor of 2 of the supremum. The proof uses second-order probability and group theory. The corollary is powerful: a random G from G certificates symmetry or asymmetry. So the recipe is simple: sample from the group, then test. How can we avoid sampling G from the group? The classical idea is covering, approximate the supremum over G by the maximum over a finite set S. But the group is large, the geometry is non-standard, and covering is non-constructive. The new idea is to exploit the group structure and its redundancies. By the triangle inequality for D, the divergence under composition G1 times G2 is at most the sum of individual divergences. This is not captured by classical covering arguments. For the rotation group SO of D, this yields dramatically reduced coverings, size order d squared over epsilon instead of epsilon to the minus d squared. This is an exponential improvement. Finally, open directions. Statistics under symmetries need theory beyond classical statistics. Can we obtain optimal reduced coverings for groups? Can we develop coverings for optimization over groups? And an exciting applied question: can we integrate symmetry testing with symmetry-aware architecture design? These remain open problems for future work. This concludes our section on symmetry validation. Now, moving to a different topic entirely. The third set of recent results focuses on the provable sample complexity benefits of incorporating symmetries into learning. In practice, learning with invariances works better. But can we actually prove that symmetry reduces sample complexity? We need a theory that works under minimal assumptions: any compact Riemannian manifold is data domain, any compact Lie group acting by isometries. Prior work often assumes the data lives on the unit sphere, and the group is a specific one like permutations or planar rotations. This is too restrictive for real applications. Our result works for any compact Riemannian manifold M and any compact Lie group G acting on M by isometries. For example, molecular conformations live on a non-spherical manifold, and the symmetry group is SE3 rotations in translations in 3D. Here is our general result. The setup: data points x1 through xn are sampled IID uniformly from a compact Riemannian manifold M. Observations are yi equals f star of xi plus Gaussian noise. The target function f star is invariant under G, meaning f star of g dot x equals f star of x for all g in G. And f star belongs to the Sobolev space Hs of M, meaning it has S-square integrable derivatives. The estimator is kernel ridge regression restricted to the invariant function class HSG, minimizing empirical loss plus a Sobolev norm penalty, only over G invariant functions. The main theorem. The expected L2 error satisfies E of the squared L2 norm of f hat minus f star is bounded by C d times vol of M mod G over N, raised to the power S over S plus D effective, where D effective equals dim M minus dim G. This reveals two distinct gains. First, a multiplicative gain: the volume of the quotient space M mod G is smaller than the volume of M itself. The larger the group orbits, the smaller this volume. Second, an exponential gain in the exponent: the rate becomes n to the power minus S over S plus D effective. Since D effective equals dim M minus dim G is smaller than dim M, the exponent is larger, meaning faster convergence. This is an exponential improvement in the sample complexity. Moreover, this rate is minimax optimal, meaning our upper bound matches the information theoretic lower bound. No estimator, no matter how clever, can do better. Let's build intuition with a simple example. Take M equals the unit circle S1, parameterized by angle theta from 0 to 2 pi. Let G be the two-element group consisting of the identity and the reflection theta maps to minus theta. The Fourier basis on the circle consists of 1, cosine k theta, and sine k theta for k equals 1, 2, 3, and so on. Now, an invariant function satisfies f of minus theta equals f of theta. Since cosine of minus k theta equals cosine of k theta, all cosine modes are invariant. But since sine of minus k theta equals negative sine of k theta, all sine modes are antisymmetric and must have zero coefficient. So only cosine modes survive exactly half the Fourier basis. This means the invariant function space has half the effective degrees of freedom. In our framework, this corresponds to vol of M mod G equals 1/2 times vol of M. The key insight: fewer surviving Fourier modes means the invariant function class is smaller. Kernel ridge regression over a smaller class needs fewer samples to achieve the same error. This is where the sample complexity gain comes from. For general manifolds, we generalize this via the extended Wales law. On a compact manifold M, the Laplace-Beltrami operator has discrete eigenvalues. The counting function n of lambda counts eigenvalues up to lambda. Wales' law for G-invariant eigenfunctions, extended by Bruning, Heinz, and Donnelly, states n of lambda is approximately omega d over 2 pi to the d, times vol of M mod G, times lambda to the d over 2. Here d equals dim of M mod G, and omega d is the volume of the unit d-ball. A key proof challenge: the quotient space M mod G often has a boundary, even when M itself does not. For our circle example, M mod G is the half-circle from 0 to pi, it has endpoints as boundary. The Newman boundary condition emerges naturally from the invariance: the derivative of f at the boundary must be 0. This is because invariance under reflection forces the function to have a flat slope at the mirror line. Also, one must carefully define vol of M mod G, since the quotient may not always be a smooth manifold, it can be an orbifold. These sample complexity results extend beyond regression to several other settings. Let me highlight the key extensions. First, optimal transport and Wasserstein distances. When comparing two distributions that are both invariant under G, the sample complexity of estimating their Wasserstein distance also improves, with the same vol of M mod G factor appearing. Second, kernel maximum mean discrepancy, or MMD. Here the story is more subtle. The gain depends not just on the volume ratio but also on the spectral zeta function of the manifold, which encodes how fast eigenvalues of the Laplacian grow. Different kernels lead to different gains depending on their smoothness. Third, these ideas extend to reinforcement learning in MDPs, where invariance of the transition kernel leads to sample complexity gains for policy evaluation. Fourth, to diffusion models, where equivariant score functions learn faster. And fifth, to geometric stability results, how robust is the gain when symmetry is only approximate. To summarize, symmetry provably reduces sample complexity. The gain is both multiplicative through volume reduction and exponential through dimension reduction. The result is minimax optimal, and the proof uses spectral geometry, specifically an extended Wales law on the quotient space. Here are the key references for further reading. Moving beyond the recent results we've discussed, let's explore a new and exciting direction: any-dimensional models with a fixed set of parameters that can be evaluated on inputs of any size. For example, graph neural networks can process graphs of any number of nodes. Deep sets handle point clouds of any size. The key question is, can we train on small inputs and generalize to larger ones? This is called size generalization. Examples include graph neural networks, deep sets, and machine learning models on point clouds, all sharing the property that one architecture handles any input dimension. How can a fixed number of parameters handle any dimension? Consider linear functions of x in Rd. A general linear function has d parameters, one weight per coordinate. But if we require permutation invariance, that is, f of x sigma equals f of x for all permutations sigma in Sd, then all weights must be equal. The function becomes w times the sum of all coordinates. Only one parameter, regardless of d. For quadratic polynomials, permutation invariance gives exactly two free parameters for any d, w1 times the sum of xi squared, plus w2 times the sum of xi xj for I not equal to j. Two parameters, independent of dimension. In general, for degree k permutation invariant polynomials, the number of parameters equals the number of integer partitions of k, which is approximately e to the power c root k. This grows with k but is completely independent of d. This is representation stability. The key insight: learn these few parameters from low-dimensional training data, then apply the exact same model to high-dimensional test data. The mathematical foundation comes from representation stability, a phenomenon in algebraic topology discovered by Church and Farb. Recent work builds on representation stability systematically. Early graph invariant networks already used size-independent parameters. Levin and Diaz in 2024 proposed a general framework for any-dimensional equivariant neural networks, combining representation stability with standard architectures. Learning theory for invariant finite-dimensional kernels avoids group averaging and learns features that generalize over size. Three key open questions drive this field. First, how to identify which problems exhibit any dimensional behavior. Second, how to parameterize models that work across dimensions. And third, how to properly evaluate models on objects of different sizes and dimensions. Applications extend beyond graphs. Any dimensional models can learn PDEs in physics, where the number of grid points varies. They apply to optimization over convex cones and graph properties like max-cut that are well-defined for any size. And in information theory, symmetry simplifies finding the capacity of feedback channels. Several fundamental open problems remain. First, identify applications and build any-dimensional models for physics, PDEs, biology, materials science, language, and sequence models. Second, do we lose expressivity? Universality is problem-specific. Some functions cannot be represented with finite parameters across all dimensions. Third, how to evaluate models on objects of different sizes and dimensions. What are the right assumptions and metrics? Here are the key references for this section. So far, we have focused on group symmetries as a source of geometric structure in machine learning. But geometry offers much more. In this final section, we explore curvature, topology, and scaling geometry beyond symmetries. Sometimes, hard-coding symmetry is too restrictive. In diffusion models, the noise distribution is perfectly symmetric. But to generate a specific image, the model must break that symmetry. This motivates a spectrum. On one end, strict equivariant models that are data efficient but rigid. On the other, foundation models that learn from scale. The promising direction, flexible symmetries that adapt to the task. This was formalized by Raya and Ambrogioni at NeurIPS 2023. Bremer and colleagues asked, if we scale up compute and data, does equivariance still help? Their answer, published in Transactions on Machine Learning Research 2025, is yes. They found that both equivariant and non-equivariant models follow power law scaling. But the equivariant curve sits consistently below, meaning lower loss at every compute budget. The gap never closes. Moreover, equivariant models benefit most from scaling model size, while non-equivariant models benefit from training longer. Equivariance provides a persistent structural advantage. Before encoding symmetries, we should check, is the data distribution actually symmetric? Lawrence, Hofgaard, and colleagues proposed a simple diagnostic at ICLR 2026. Take your dataset. Augment it with a random symmetry transformation. Then train a classifier to tell original from augmented. If it succeeds, your distribution breaks that symmetry. They tested standard benchmarks. QM9 shows high symmetry breaking. OC20 was even canonicalized, hiding the problem. The theoretical implication, when the distribution breaks symmetry, forcing invariance can hurt performance. The manifold hypothesis says real data lives on a low-dimensional manifold inside high-dimensional space. If true, we might hope to escape the curse of dimensionality. But is low intrinsic dimension enough to guarantee learnability? Kiani, Wang, and Weber proved at NeurIPS 2024 that the answer is no. Bounded curvature alone does not make learning easy. It remains hard in the statistical query model. They identified three regimes. First, manifolds with positive Ricci curvature and bounded volume, like spheres, these are efficiently learnable. Second, manifolds with bounded curvature but unbounded volume, these are provably hard. Third, heterogeneous manifolds with mixed properties, this is real-world data, and remains an open problem. Topology gives us another lens on data geometry. Instead of just nodes and edges, topological deep learning uses simplicial complexes with higher-order cells, triangles, tetrahedra, and beyond. The standard framework is higher-order message passing, or HOMP. But HOMP has fundamental blind spots. Aiton, Gelberg, and colleagues proved at ICLR 2025 that HOMP cannot detect important topological properties, diameter, orientability, planarity, and homology. These are inherent limitations, not implementation bugs. To fix these blind spots, multicellular networks, or MCN, achieve full expressivity using ideas from higher-order Weisweiler-Leman tests. But they are computationally expensive. The scalable variant, SMCN, trades a little expressivity for practical efficiency, and outperforms both HOMP and standard GNNs. Here is a key example. A torus and a Klein bottle look the same locally. Same cells, same neighborhoods. The difference is orientability. On a torus, edge identifications are consistent. On a Klein bottle, one pair of edges is reversed. HOMP gives the same output for both. MCN and SMCN can tell them apart. The presenters acknowledge support from Telos, the Humboldt Foundation, AIVO, and their many collaborators at MIT, Harvard, and TUM. Thank you for watching. This video was produced as a lab assignment and may contain errors or inaccuracies. Please refer to the original tutorial slides and papers for authoritative information.